We'll continue on the divergence theorem, though this is really just a review day. Just a chance to do more examples, that sort of thing. First of all, let's review what the divergence theorem says, at least stated a little differently. It is the triple integral over a three-dimensional region E of the divergence of a vector field f dv, whether that dv is dx dy dz, or eventually a rho squared sine phi d rho dv d theta, something like that, okay, is the same as the following surface integral. So it's the integral over, and the surface is the boundary of E, of the flux of f. So f dot n ds. Okay, there's the divergence theorem. Really, this next question could be just truly done as a warm-up, meaning let's write down the question and then pause and give it a try on your own. Okay, so let f be the following vector field. So x comma y comma z squared. Let S be the surface consisting of the following three pieces. So first off, there's x squared plus y squared less than or equal to 9, but only when z is equal to 8. There's also x squared plus y squared less than or equal to 9, but only when z is equal to 2. And finally, there's x squared plus y squared is equal to 9, but only when z is between 2 and 8. So then the thing to do with that much a setup is to find the flux of f across this oriented surface S, okay, oriented outwards. And I'd like you to try doing this two ways. So part A, do this directly, and then part B, do this using the divergence theorem. I'd say if you really want to get something out of what's going on, pause the video and try both of these, or get as far as you can on each of these individually. That way, when you compare what you have to what I have, you can check your work. Maybe, I guess, just one thing that you might try to do is wait to pause until you see the parameterization that I have in mind for part A, just because there are so many parameterizations that can work, right? So, for instance, the surface, by the way, just to draw a picture real quick of the three pieces of the surface together, it ends up creating the shape of a cylinder. It's not filled in though, right? It's a hollow cylinder. So you have the circle on the top, you have the circle on the bottom, and then this last piece here describes all the part around. Like if you had a soup can, it'd be the label of the soup can. So I would say let's parameterize the surface on the top in the following way. I mean, there are lots of options, not the least of which is just switching the two parametric variables. But the top surface could be parameterized by r of u comma v is equal to angle bracket u cosine v comma u sine v comma 8, with parameter domain u going between 0 and 3, right? U representing the radius. Go up to radius 3 because of the 9 on the right side of the inequality. And then v going between 0 and 2 pi. So this might be a decent place to pause. You can guess how my parameterization of the circle on the bottom is going to look. Okay, so then let's go through these steps, and you might have some of the steps in a different order. R sub u is cosine v comma sine v comma 0, and r sub v is negative u sine v comma u cosine v comma 0. And the cross product, we will not work out all the detail here, but it will turn out to be 0 comma 0 comma u. And if we look at the magnitude of that vector, we should end up with, root 0 squared plus root 0 squared plus u squared. So that will just be the absolute value of u, which, because u is only between 0 and 3, is just going to be u itself. For a an orientation, should be plus or minus this 0, 0 u vector divided by u. So in the end, it's either going to be plus or minus 0, 0, 1. Now we could have just really seen this from the picture that for the outwards, we're going to need the outwards here is going to be upwards for the upper surface here, right? So this is going to have to, in this case, we really are going to need the 0, 0, 1 vector there. Okay, and so then in this case, d capital S is going to be this u right here times du dv. Okay, let's take a look at the surface on the bottom. This is parameterized. The surface on the bottom is parameterized by r of u comma v is equal to u cosine v, u sine v, comma 2. And parameter domain u from 0 to 3, v from 0 to 2 pi. The RU, RV business should all work out the same. That part I'm just going to actually copy paste. That should all work out the same way. You're just differentiating 2 instead of differentiating 8. One thing that's going to work out differently, though, is that the n vector here is going to have to be the minus sign, because we're orienting the circle on the bottom here downwards in order to get an outward orientation. So negative 0, 0, 1. And ds, nonetheless, here for this part, is still going to be this u right here, u times du dv. Okay, we still have one more piece, and it's the part that's around this way. It's the label of the can, so to speak, right? So there's one more surface. There's this third surface. It's the side, where the label is, and this is parameterized by, for instance, one option for r of u comma v here would be 3 cosine u, 3 sine u. So the thing is, the radius of the circles that we are exhibiting or noticing right now are always 3 for the label itself. It's just, we'll see that the height changes. So the u here is now acting as an angle. Yeah, so now it's unlike earlier where u was the value of, the radius off the in just the sense of the xy plane. Now u is between 0 and 2 pi. It's just because you can do it this way. If you don't like this, you can switch the roles of u and v. V, which is just the z coordinate, is going to go between 2 and 8. Ru will work out to be negative 3 sine u, 3 times cosine of u, 0, and Rv will work out to be 0, 0, 1. The cross product of Ru, Rv works out, we won't show all the details here, but it'll work out to be 3 cosine u, 3 sine u, 0, and then the magnitude of this resulting cross product is, okay, so you might see the shortcut, but I'm just going to write this out. 3 cosine u quantity squared plus 3 sine u quantity squared. So inside, once you rewrite the squares, so 9 times cosine squared u plus 9 times sine squared u. So you factor out a 9 and you have cosine squared u plus sine squared u inside parentheses, which just simplifies to a 1. And so this will end up being 3. An orientation for this surface. So we'll have this 3 cosine u, comma 3 sine u, comma 0 over 3. So we'll have plus or minus, once you go ahead and do the scalar multiplication of the 1/3, cosine u, comma sine u, comma 0. You might have already actually seen this in a sense from the picture. You could certainly see that the 0 makes sense because the vectors that we're looking at need to uh, have no height to them in a sense. Like if we look at just drawing the can, then we're talking about like, you know, let's say right here, we need a vector that points that way. If let's say if that's the x-axis, that's the y-axis, that's the z-axis. Oh, that was not the best of diagrams. Okay. Um, you have to imagine this can is 2 units off of the ground, so to speak. Yeah. Based on the way that this needs to point, right? This needs to point out this way with just to spot check, this location right there would be u, the angle would be 0 radians. So um, if we need the vector there to be, so we need, I mean, we can actually by inspection see that this vector really needs to be 1, 0, 0. So the way we get literally positive 1, 0, 0 is to take the plus sign here. Yeah, so we can see really from the picture that we need to use n should really be the plus cosine u, comma sine u, comma 0. It's a geometric thing, as so many things we're seeing really here need to be. Then ds will be this 3 over here times du dv. Okay, we've got all the major pieces in play. Now what we should do is to compute the integral over the surface S of the flux. This is going to split up into 3 separate integrals simply because there's 3 separate surfaces that had to be parameterized separately. There was just no way to parameterize them all together at the same time. So there's the integral over the surface that was the top of x, y, z, z squared dotted with its normal vector, which was 0, 0, 1, recall, plus the double integral over the surface that's on the bottom of still same vector field x, y, z squared, now dotted, however, with 0, 0, negative 1, right? Because now the vector pointed downward, right there, plus the integral of the surface that's the side around, like the label of the can, and same vector field, so x, y, z squared, but now dotted with this thingy right here. So we'll just copy that down in place. And there's some certain mishmash of variables right now. We'll certainly have to take care of all these things. So cosine u, comma sine u, comma 0 ds. Now we've got some cleanup to do. So first off, let's make things as nice as possible. X times 0 plus y times 0 plus z squared times 1. Yeah, so integral over the surface on the top, z squared ds, plus same deal for the integral of the surface on the bottom. We'll have a negative z squared as the integrand there, ds. For the next term, now we'll have 0 here times z squared, and then we'll have x times cosine u, but the x, if we just scroll up for a moment, ought to be replaced with this 3 cosine u up there, right? So we'll have well, let's do that in a future step. We'll go ahead and mix. We'll just have x times cosine of u plus y times sine of u ds. Okay, just note that the x right there is going to be 3 cosine u, while the y here is going to be 3 sine u. So because of the scrolling I'm going to need to do, let me just copy down here that this is going to eventually turn into 3 cosine u, and that the y we see right here is going to, in a moment, turn into 3 sine u. Okay, so we'll have integral, leave a little space between the integral signs. The z value here gets replaced with the z component of the parameterization way up here, which was 8. Then for the second integral, we're going to instead put in a 2 there. So here there's going to be an 8 squared, and then ds, recall, was right here, u du dv, u du dv, and u went from 0 to 3, and v went from 0 to 2 pi. For the second integral, same deal, 0 to 2 pi, integral 0 to 3, copy the minus sign. However, in the parameterization, z was 2, so we'll have 2 squared. ds, though, was just like in the previous integral, u du dv, plus, in this last integral, we'll have, let's go with ds still here, yeah, 3, let's leave a little bit of space, 3 du dv. U is on the inside, which, sorry to do this, went from, u is the one here that went from 0 to 2 pi, and v was the one that went from 2 to 8. Let me just scroll up slowly so we can point that out right there. Okay, and then we need to write the rest of what appears right here in this space. The 3 was, just recall, part of the ds, okay? So we'll replace the x and the y in the ways that we said we would right here. And so we'll have 3 cosine squared u, right? So yeah, 3 times cosine of u times cosine of u, plus 3 sine squared u. Oh, this is going to work out very nice now. So the thing to note here is we're going to have so we'll copy the 8 squared. We have this u squared over 2, but then the over 2 is going to actually cancel with eventually times 2 from the 2 pi. So we're actually going to end up with times pi times 3 squared. You can work out some of the details there. We're just speeding things up a little bit. Copy the minus sign first here, and in the same way, we're going to have 2 squared times pi times 3 squared. And then for the last term, well, look, if you factor out the 3 here and here, you end up with a 9, right? Cosine squared u plus sine squared u is just going to simplify to 1 anyway. So you're really just integrating the number 9 from 0 to 2 pi, so that'll create a factor of 2 pi. And then from 2 to 8, see, the variable really effectively doesn't appear there because you're just integrating a constant. If we work out some of these details, this will be 9 pi times 8 minus 2 times 8 plus 2. There's just, I won't bother really simplifying this in too creative a way or explaining all these steps. There's lots of ways to do the arithmetic that gets you here. So what, 9 pi times 6 times 10 plus 108 pi. So 554, times a 10, so 540 pi plus 108 pi. In the end, that is going to be 648 times pi. 648 pi, huh? That's a lot of pi. Okay, so that computes the flux in the direct method. Now, what happens if you use the divergence theorem instead?